Okay, here we go. Lesson 910, last lesson in the sequence and series chapter. That's exciting. Okay, so we're going to start off with lesson 9.7 pretty much. Lesson 9.7 was about creating Maclaurin or Taylor polynomials. A Taylor or Maclaurin series is a polynomial of infinite degree. So let's try to represent that pattern using all the techniques that we've already learned to create a Taylor polynomial. Actually, in this case, a Maclaurin polynomial because it's centered at 0. You need to find the first several derivatives. I'm just going to find the first few. Okay, so our function is sine of x. The first derivative is cosine of x. Second derivative, negative sine of x. Third derivative, negative cosine of x. Fourth derivative, we're back to sine of x, and then that pattern is going to continue to repeat. We want to evaluate each of these at the center point, 0. Okay, so sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine of 0 is negative 1. Sine of 0 is 0. The next one will be 1, 0, negative 1, 0, 1, and so forth. So we're ready to write our polynomial, Maclaurin polynomial, but toward infinity makes it a series, okay? So this function, sine of x, equals, well, we have 0 plus the first derivative times x, plus the second derivative divided by 2 factorial, x squared, plus the third derivative divided by 3 factorial times x to the third, plus the fourth derivative times x to the fourth divided by 4 factorial, plus the fifth derivative times x to the fifth divided by 5 factorial. And that pattern is going to continue toward infinity. Can you generalize that? Well, to generalize it, it's a good idea to think about what you can start off with. Okay, so if I start off with 0, I know that that's an odd degree. So I'm going to have x2, the setup for an odd degree. Okay, so if this is going to be from n being a 0, and n being a 0 gives me a 1, n being a 1 gives me a 3, n being a 2 gives me a 5, that'll help create the setup. Okay, so that's going to be x to the 2n makes it an even exponent, and then plus minus 1 is going to make it odd. So 2 to the first is 2, I would add 1 to get the n to become the correct exponent. 2 times 2 is 4, plus 1 is 5. 2 times 3 is 6, plus 1 is 7. So I know I have it set up correctly, and then I would have 2n plus 1 factorial in the denominator. So I'm trying to come up with this generalized statement. And there are other versions. This is the version I came up with because I'm starting with n being a 0. That's what I chose. I could start with n equaling a 1. And it's going to look slightly different. Okay, I need the alternating aspect. So I'm going to have a negative 1 to a power here. And when I plug a 0 in, it needs to be positive. So I can make that just to the n power. When I plug a 1 in, it's going to be negative. So I've confirmed that's correct. So this would be the Maclaurin series representing the sine function. Okay? Now we should be able to come up with the radius and interval of convergence just like with all of these power series. So ratio test would work for this. I think we might have done this in a previous lesson, but we can review it. So the ratio test would give us the limit as n goes to infinity of the n plus first term, so that's x to the 2n plus 3 over 2n plus 3 factorial, divided by the nth term or times the reciprocal. And remember, this is the absolute value, which is why I don't include that alternating aspect. Okay, so that's going to be the limit as n goes to infinity, and this is going to simplify to be x squared on top, 2n plus 3 times 2n plus 2 on the bottom because of the factorials canceling. And as n goes to infinity, this approaches 0. So our r is 0, which is less than 1. It converges no matter what the x value is. That means my radius of convergence is infinity, okay? So the interval of convergence would be negative infinity to infinity. It doesn't matter how far away you go from that center. Okay, so we just created this Maclaurin series representing sine of x. This is what we're dealing with. Now, if we just memorize that pattern, I don't have to go through all that thought process. It's not a bad pattern. It's all of the odd exponents. I'm dividing by the factorial of that exponent, and it alternates signs. You can remember that. And then if you need to come up with this scenario, you can come up with that. So that's going to allow me to get to the answers much quicker, to get to my series much quicker. Just learn some of these basic ones, okay? Now the next example deals with the fact that this series does not approximate the function, it gives me the exact answer of the function. So this convergence of a Taylor series basically says that if the limit as n goes to infinity of the remainder is 0, that means the remainder is getting closer to 0 as you approach infinity. That means that this Taylor series or Maclaurin series converges, and it is what f of x is, okay? So example 2 says to show what we just worked with, show that this Maclaurin series is actually sine of x. It doesn't approximate it, it equals it. So to show that, we're going to be working with the remainder, okay? We know that the nth remainder of this series is larger than 0 or equal to 0, okay? It's an absolute value, it's not going to be less than 0. That nth remainder is equal to the n plus first derivative evaluated at z divided by n plus 1 factorial times x to the n plus 1. Okay? And because we know the derivative, okay, we know that it doesn't matter what n we're on, the n plus first derivative of z is either positive or negative sine of x or positive or negative cosine of x, because it just alternates between those four, right? And that means that the absolute value is definitely going to be less than 1, because that's the largest value for sine of x or cosine of x. So because of that information, I can make the statement, and I'm going to erase this. I can make the statement that this remainder that I just came up with is less than or equal to 1 x to the n plus 1 over n plus 1 factorial. Okay? Well, this part right here, the limit as n approaches infinity of this term approaches 0. It becomes 0, and that's because of the order of growth. This is a polynomial factorial. Factorials grow faster than polynomials. That's going to approach 0. So if you see what we have set up here, we have 0 is less than or equal to this middle mess, which is less than or equal to 0. So by the squeeze theorem, our remainder is 0 as n goes to infinity. Okay? That means that the sine of x is equal to, not approximated by, the summation as n goes from 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. That is an equals statement, okay? All right, so if you turn the page, you probably can look ahead there. We have a big box of series. We're heading there where we're just gonna memorize them. And we have actually seen a lot of them show up in the homeworks that we've done and the notes that we've done. And you might have been recognizing some of those simpler patterns, okay? Now, why is this beneficial? Example 3. If we know some of the series, it makes the complicated ones easier, okay? So, this problem says, find the Maclaurin series for the function sine of x squared, okay? If I didn't have what I'm going to use today, to create a Maclaurin series, I would have to find the first derivative. It's a Maclaurin, it's centered at 0, right? The first derivative would be cosine of x squared times 2x, because of the chain rule. The second derivative would require the product rule. The first times the derivative of the second, which would be a negative sine of x squared times 2x. So the first times the derivative of the second plus the second times the derivative of the first, which gives me a negative 4x squared sine of x squared plus 2 cosine of x squared. And then if I want the third derivative, I have a product rule and plus this. And just this derivatives are really messy. It takes a long time to figure that out using this procedure, okay? So because that's difficult, we can use the fact that we know that the sine of x, not this other version, just the sine of x, the one that we just worked on, is equivalent to, well, the expanded form would be x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial. It's all the odds. They all alternate. So in other words, that's negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. When you generalize that statement, well, we learned a property of series, of that sigma notation, that if I have the sine of x and the sine of x squared, that just means I can plug x squared in. That's going to mean I have x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. Because what we're doing is we are plugging x squared in. X squared is getting raised to that exponent. That's going to simplify to be negative 1 to the n, x to the 4n plus 2, because you multiply exponents when you have a power to a power, divided by 2n plus 1 factorial. And then you can write it as the sigma notation stuff, the sum as n goes from, what were we starting with, 0? If I remember correctly. Yeah, we're starting with 0, right? You can just confirm, if I plug 0 in, I get my x squared term, right? So n equals 0 to infinity. That is a much easier way of coming up with a series for sine of x squared. Use what you know about sine of x and manipulate it a little bit.
One moment. Okay.
No, Siri thought I was talking to her. Okay, so down to example 4. Example 4 is a really tough problem. It's getting into one of the series that we're just going to memorize because it's so inconvenient, okay? And for sake of time, I'm not going to do that. If you'd like to see that, you can ask me in class, and I'll go through that one. But it allows us to do example 5. So to do example 5, I want you to jump to the next page. Example 5 deals with a 1 plus x to the 1/3 power. And you see the very bottom of the boxed in series, we have a series that represents 1 plus x to a power. So I'm going to just use the known series. If I have it memorized, it's not a bad pattern, guys. So I have 1 plus x to the k ends up being 1 plus k times x plus k times k minus 1 times x squared divided by 2 factorial plus k times k minus 1 times k minus 2 x to the third over 3 factorial. And what's happening is, not in general form here, but I'll show you what that is. I'm taking whatever the k is times 1, or that number minus 1, times that number minus 2, until I get to k minus n minus 1. That's always 1 less than whatever exponent you're on. So if I'm on n, I'm going to subtract an n minus 1. That would be the last factor in that product, x to the n over n factorial. So this is the generalized form that I could write with the sum as n goes to infinity. N starting with 0 and going to infinity. Okay, so in example number 5, we have 1 plus x to the 1/3 because it's a cubed root. So using what we just created here, we would have 1 plus 1/3 x plus 1/3 times negative 2/3 x squared over 2 factorial plus 1/3 times negative 2/3 times negative 5/3 x to the third over 3 factorial. Let's do one more. 1/3 times negative 2/3 times negative 5/3 times negative 8/3 x to the fourth over 4 factorial, and it would keep going. Okay, well, if we do some simplifying, I might be able to come up with a generalized version that's a little more simplified than that. Okay, so let's see what's happening here. Well, they're alternating eventually. Okay, so I have 1 plus x over 3. Okay, I got that so far. Here's where it starts alternating. Minus, I'm going to write this as 1 times 2 x squared over 3 squared times 2 factorial. I'm trying to come up with a pattern that I can represent. So I'm looking at patterns up here. It's going to be a plus next. I got 1 times 2 times 5, x to the third, over, that's going to be 3 to the third times 3 factorial. One more, this is going to be a minus now. 1 times 2 times 5 times 8, x to the fourth. It's a 3 to the fourth, 4 factorial. I'm trying to connect the n with some of the patterns. There's 4 threes that I'm technically dividing by. So can I generalize this at all? Well, I know it's going to be 3 to the n. It's going to be an n factorial. It's going to be an x to the n. I got all those pieces there, right? Because this is 0, 1, 2, 3, 4, trying to make that connection. All right, so then the rest of it, okay, so I'm adding 3 every time. When you're adding a number every single time, it's actually going to be the pattern 3 times n. Okay, but then you have to fix it because I need to have an 8. Well, 3 times 4 is 12, minus 4 would give me my 8. So the pattern on the top is 1 times 2 times 5, and it keeps going until you get to the 3n minus 4. That would be your last term. Okay? That's the sum as n goes from 0 to infinity. Let's just make sure it gives us all of the problems. If I start with 0, it doesn't work. I'm going to start with 1. If I start with 1, it doesn't work. It doesn't give me my x over 3. I'd have to start with 2. 2's the first one that works. Okay, So you're just establishing, okay, eventually this is the correct pattern. And I'm missing one more thing. I'm missing my alternating part. I'm just going to put it on the end here. It's going to be -1 to the, this needs to be an odd number, or a negative number. So -1 to the n plus or minus 1, it doesn't matter. That's going to be our rate, because when you plug a 3 in, it becomes positive there. So this is correct, and it gives me all of the terms except the first two. So this is what I got. 1 plus x over 3 plus, there's the rest of it. Okay, that's how you can handle that. Okay. So, the power series. For elementary functions, you should know these. We got our 1 over x function at the top. We've done those. That's a simple expansion. 1, they're alternating. 1 times x minus 1 plus x minus 1 squared minus x minus 1 cubed. It's centered at 1. The second one is kind of the same pattern, but now it's centered at 0. Okay? The third one is actually the antiderivative of the first one, so you don't have to necessarily memorize both of them. You can memorize one, do either the derivative to find the first one, or do the antiderivative to find the third one. E to the x, that's a simple pattern. All of the exponents, and you have your factorials in the bottom. So 1 plus x squared over 2 factorial, x cubed over 3 factorial. Then if you take that, the sine of x, those are all of your odd exponents, alternating. Cosine of x, those are all your even exponents, alternating. Arctangent looks almost identical to sine, except you don't have factorials. Okay? Arcsine is not really an important one. We don't use it that often. Okay? You'd be able to look that one up. And then the last one, hopefully you can remember that. So, the next few examples, we're going to use those known series to get some more complicated ones. We kind of did this process for the sine of x squared, for example 6. So if you want to give it a shot, you can pause the video and try it, or you can listen and then try some in your homework and get your practice there. So example 6, I'm trying to come up with a power series for the cosine of the square root of x. Well, I know the cosine of x power series is, so cosine, those are the even ones. So that's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, x to the 6th over 6 factorial. So it's really the pattern x to the 2n over 2n factorial. And I forgot the alternating part again. I need a -1 to the n in front. -1 to the n. Okay? So, if I want the cosine of root x, that just means plug the square root of x in there for all of the x's. So 1 minus, the square root of x squared is x over 2 factorial, plus the square root of x to the 4th is x squared over 4 factorial, minus the square root of x to the 6th is x to the 3rd. So that's going to change this part to be the square root of x, or x to the 1/2 to the 2n. It just becomes x to the n. Or you might have seen that in this pattern. It just becomes x to the n. So let's write it using our sigma notation. The sum as n goes from 0 to infinity of -1 to the n, x to the n, over 2n factorial. Starting from a known power series, we can manipulate it a little bit to get the series that is desired. Okay? So example 7 asks us actually to do a multiplication problem and to find a series for that. You're not going to like this one, but it's not too bad. Okay, we're supposed to find something for e to the x times the arctangent of x. That's the function we want to represent. So that is going to equal our e to the x function, expanded. E to the x is 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial, x to the 4th over 4 factorial. I don't know how many of those I need. That's my e to the x. I'm supposed to multiply by arctangent. Okay, arctangent, that's going to be x minus x to the third over 3 plus x to the fifth over 5 minus x to the seventh over 7, and that pattern continues. So all I'm doing is I'm foiling this. It says find the first 3 non-zero terms. I just have to do this far enough until I have the first 3 terms of the result. So I'm foiling. 1 times x is x. 1 times this is negative x to the third over 3 plus x to the fifth over 5 minus x to the seventh over 7. I'm going to stop there. I might need to go further. But I did 1 times each of those plus x times each of those. I like to set up and line up my terms when I do this. So x times x is x squared. All right, that's going to go right in between here, x squared. X times x cubed over 3 is x to the fourth over 3. It's right in between those. That's x to the sixth over 5. And I would keep going if I need to, so I might need to keep going with the x's, okay? Now I'm going to distribute this guy. That's x cubed over 2 factorial. That lines up with this guy. X cubed over 2 factorial. We then have x to the fifth over 2 times 3 over 6. X to the fifth over 6. Okay, then we have x to the seventh over 10. Okay, now my next one, I would have this times this, that's x to the fourth over 6. And I know I don't need to go any further because if I'm combining my like terms, the further I expand it, the further down the line I get. Okay, so I get additional terms that are beyond my first 3 non-zero. So x is my first one. X squared is my next one. I want to combine these. Okay, so that's minus 2/6. 1/6 minus 2/6 is negative 1/6 x cubed. That's technically as far as I need to go. But I have enough information, I can get one more. And that's going to be 2/6 plus 1/6 is 3/6, or 1/2 x to the fourth. And then that pattern, we could keep getting more and more terms. Okay. 3 more problems here. Letter B is tangent of x. So tangent of x, there's no formula for that, but there is a formula for sine, and there is a formula for cosine that's a known series. So I can create tangent from sine and cosine, I just have to divide them. So, dividing by cosine, I'm taking my sine sum, which is all of the odds, so that's x minus x to the third over 3 factorial. Right? Sine, yeah. Okay. Plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so forth. I need the first 3 non-zero terms again, and I'm dividing that by cosine, which would be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. Hopefully that's enough. Okay, now when you divide polynomials, what do you need to multiply 1 by to get x? You have to multiply by x. So I get x minus x to the third over 2 factorial plus x to the fifth over 4 factorial minus x to the seventh over 6 factorial, and that would keep going. And we subtract all those lines, so that makes those cancel. You're subtracting all those lines, so we have 1/2 minus 1/6. So 3/6 minus 1/6 is 2/6, or 1/3 x to the third. Okay. Then we have some fractions that I need help with. So I'm going to go to my notes here. That's going to end up being a negative 1/30 x to the fifth. and then a plus 1/840th x to the 7th. That's what you get when you add and subtract those terms. Now we do it again. 1 times what gives me this? Times 1/3 x to the 3rd. That's how I get that. So I do all my multiplying. I get 1/3 x to the 3rd. I get 1/6 x to the 5th. That's a 24. So 3 times 24 is 82. Where am I here? 72. Okay, so minus 1/72. Sorry, that's plus 1/72 x to the 7th. Okay, and we're subtracting that line. That's why my notes confused me. I already had my minus signs in there. All right, so those cancel. This gives us 2/15 x to the 5th minus 4/315 x to the 7th. And I'll have to do this one more time to get my third non-zero term. So 1 times 2/15 x to the 5th will get me to the next line, and that's as far as I need to go. Okay, so that's a series for tangent. Whew. Takes a lot of work, but it's just algebra. Okay, keep track of your numbers. You guys can handle it. All right, so the next one we got sine squared. This is example 8. How can we come up with a function for sine squared? Well, sine squared is equivalent to 1 minus cosine of 2x over 2, or 1/2 minus 1/2 cosine of 2x. I can come up with cosine of 2x. That's the only part I need to worry about, okay? So, the cosine of x, those are the evens, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so forth. So in general, that's negative 1 to the n, x to the 2n over 2n factorial. And all we have to do for that known function is plug 2x in. If we plug 2x in, we're going to have 2x's getting squared. So 4, let me leave it as a 2, okay? So 2 squared x squared over 2 factorial plus 2x to the 4th, that's 2 to the 4th x to the 4th over 4 factorial. So in general, it would be, I'm plugging 2x in, 2 to the n, x to the, 2 to the 2n, x to the 2n, over 2n factorial will be the general form of that. Okay? So, if I multiply by negative 1/2, if I distribute my negative 1/2 into that, I get negative 1/2 plus, right, because I'm distributing negative 1/2, 2x squared over 2 factorial minus 2 to the 3rd x to the 4th over 4 factorial. So what's happening here? It's now negative 1 to the n plus 1. It's now 2 to the 2n minus 1. X to the 2n over 2n factorial. Okay, because that's what's happening here. That's always one less than that one. Okay, so if I add a 1/2 to that, right, I'm adding 1/2, I'm adding 1/2, that term actually goes away. I'm left with 2x squared over 2 factorial. Something's wrong there. No, it's not. That's right. 2 cubed x to the 4th over 4 factorial negative 1 to the n plus 1, 2 to the 2n minus 1, x to the 2n over 2n factorial. Okay, so if I wanted to write that using sigma, it'd be the sum of negative 1 to the n plus 1, 2 to the 2n minus 1, x to the 2n over 2n factorial. But what do I start with? Because that first term canceled. I actually want to start with a 1. So with n equaling 1 to infinity. Okay. Last problem. Says to use a power series to approximate the integral 0 to 1 with an error of less than 0.01. So we have to have a specific accuracy when we make this approximation. We did this before, but we had to come up with our series using the technique of creating the Maclaurin. We couldn't use a known series, but we can use a known series now. I know the series for e to the x is 1 plus x squared over 2 factorial, x to the third over 3 factorial, x to the fourth over 4 factorial. In general, it's x to the n over n factorial. So I got that. I want e to the negative x squared. So I replace all the x's with negative x squareds. That's going to be 1 minus x squared plus x to the fourth over 2 factorial minus x to the sixth over 3 factorial plus x to the eighth over 4 factorial. So that pattern would be negative 1 to the n, x to the 2n over n factorial. Okay? So that's the function I'm dealing with. This says to integrate from 0 to 1. That function. So that's going to be the integral of this. So it's going to be x minus 1/3 x cubed plus 1/10 x to the fifth, because I'm dividing by 5, minus, so it's going to be 7 times 6, 1/42 x to the 7th plus, I'm going to keep going. Now I don't exactly know how far I'm going to go. I'm evaluating it from 0 to 1, but see it's an alternating series. I'm going to use the alternating series test. So all I have to do is find the term that is 0.01 or less, okay? Right now, if I plug my 1 in, and then plugging a 0 in doesn't do anything. So plugging 1 in is how I'm getting my values. If I plug a 1 in, I get 1/42. 1/42 is 0.02, okay? So that's not within my standards. I need to go to the next one. So the next one would be the antiderivative of this. Okay, so that's going to be an x to the 9th. An x to the 9th, we need to divide by 9. So that's 24 times 9 on the bottom, which is 216. So we get 1 over 216. That's 0.005. So if you actually find your values here, that's negative 0.3, that's 0.1, okay? This ended up being 0.02, this ended up being 0.005. That's the first one. My first excluded value. So all I have to do is the sum of these 4 terms, because that term is within the accuracy. That's what the alternating series test says. So by the alternating series remainder. By the alternating series remainder, we add the first 4 terms to have accuracy of the 5th term, 0.005. Okay? Now, if you actually add up and use this integral, you add up those first 4 terms, you get that your integral from 0 to 1 of e to the negative x squared dx is approximately 0.74. And I probably should not have 2 decimals. I need to have 3 decimals. Let me get that third decimal on there. So we are taking 1 minus 1/3 plus 1/10 minus 1/42, and it's 0.74. Oh, I know why I rounded it, because it told me to be accurate to 2 decimal places, 0.01. That's why I rounded to 2, because that's what the direction said. It's 0.742857, but we can only say it's as accurate to the 5th number, so those other digits aren't really relevant. Okay. All right, that finishes it. We did it. We just need to practice and get this stuff in our head. Learn those, most of those formulas on that box. E to the x sine of x cosine of x, 1 over x, 1 plus x to the k, arctangent. Those are the really important ones. Natural log of x we can figure out. And yeah, we'll go from there. Do the homework, bring your questions, and we'll hit the review sheet. Okay? See you later.